Hi, everyone. So I decided to take to slow down a little bit and to say a few more things from last time again. So instead of jumping straight into Morse theory, we'll spend just a few minutes explaining two things. So first of all, I want to finish the proof. Well, actually, I'll do that second. First of all, I want to go back to the example where we found a cobordism, a framing for a cobordism going like this that connected 2 points that went back. I just kind of want to write down the formula. I don't know if you managed to do that or not. It's not very hard, but I think it's still worth saying a few words. So, basically the picture we had was, we have a bunch of points, and this is true. Basically, this is still in a way part of the proof of the Hopf-Degree theorem. So if you have a bunch of positive points here, a bunch of positive points here, negative points, you connect all the positive points, you connect all the negative points, and then you might have some positive and negatives that remain on one side or the other side. And say, for example, it's on this side, and I'm just going to do for 1, because that's enough for you to see what's happening. And then I need to show that, so if this is positive and this is negative, I can connect them with the path like this. And I have a framing that will basically restrict to the framing here and to the framing here. And as I explained last time, choosing an orientation for a point gives rise to basically a bunch of framings, but they're all equivalent because an orientation is an equivalence class of bases, where the equivalence relation is isotopy. And if you have an isotopy of bases, then that will give you a framed cobordism. I explained that last time. So there was just one little point that I kind of didn't finish the calculation because we had the problem where we started the path by not moving, and then we had a zero derivative, and we couldn't split up the tangent space. So anyway, the way to fix it is pretty simple, but I think it's still kind of worth saying, at least what my idea was. Maybe you have a different idea. But anyway, so this path, last time I called it sigma. I kept wanting to try to call it sigma, and it was eta on my notes. So maybe it's better not to use the notes. So anyway, so this was actually the sigma tilde. So last time I called this P2 and P3, so maybe let's keep using that notation. And my sigma tilde was the following path. It was basically, first I had a path sigma from 0, 1 to x, where sigma restricted to 0 epsilon was equal to P2, and sigma restricted to epsilon, 1 minus epsilon 1 was equal to P3. And you could, so now what you could do is, you can also assume, for example, it's not completely necessary, but we could, for example, suppose that sigma prime is different from 0 for t in epsilon 1 minus epsilon. So I want a path that is going to be stopped near P2, but then I want to kind of call epsilon the place after which it actually starts moving. Okay? And it's actually not hard to to think that you can suppose also that this vector it's kind of converging in norm. So this guy converges. This limit exists for t going to to 1, going to epsilon. So this exists, and the limit of sigma prime over norm of sigma prime as t goes to 1 minus epsilon, I guess plus and then minus. These two limits exist. Okay? So of course, if I have this condition, then sigma prime at epsilon and anything smaller is going to be 0. But I can assume that that the unit vector of sigma prime is converging to something as I get close to this limit. Okay? So that's just saying, you can think of this function as I have a fixed direction, And then I start with a speed. My speed, is 0, and then kind of goes like this. So that, for example, if like near P2, I had some fixed vector W, a unit vector, in, say, Sn, or, well, yeah, I mean, this isn't some norm. I guess, yeah. Oh, no, that's OK, because I have a Riemannian metric. Yeah. So I have a Riemannian metric, so I can divide by the norm. And this is not in Rn. This is in the tangent space of X. So anyway, like I can think about sort of having, I mean, if I'm in Rn, I can take some vector, in Sn, and I could consider a path that is just a function times W plus P2. So this would be in Rn. But this is kind of exactly the same thing, but in a manifold, like using a chart. Locally, you could say, and where the function f, it looks like this. So it's constant, it's 0 for a while, and then it kind of goes up exactly at epsilon. So you can always do that. I mean, you can actually build this function by hand. Okay, but I think it's still worth saying this thing. And the reason I want to assume that is, well, you'll see in a little bit. So then, we defined sigma tilde to be, so there was a function of t, and then there was sigma of t. And this function, I kind of used the function t1 minus t. But anyway, it's just a function that goes like this. And then I said, well, OK, now I want to find an isomorphism from the tangent space of X. The tangent space of X to the tangent space of the point, at least at the point sigma of t, to the tangent space of sigma tilde of sigma tilde of t. So that's what you want to do. OK? And then, OK. And then here, clearly, there's along this path, you can just take any basis and you kind of have there's an obvious way to move it around. And, for example, sort of there's this trivialization that's given by the path. So all they have to do really is construct a canonical isomorphism of this form. OK? So how do we do that? So, so I said, take a vector v here. And, my idea was you write it up as a, you decompose it in the direction of sigma prime and then in the orthogonal complement. But the problem with that is that the orthogonal complement of sigma prime, like if sigma prime is 0, then that doesn't work. So, instead of using sigma prime, what you can do is you can let W of t be a vector field along sigma such that, so the unit vector field, a unit vector field, such that W prime, such that W of t is always parallel to sigma prime. I mean, this is very simple, but what this is saying is like, it's just taking care of the points where sigma prime is 0. So as you get close to sigma prime, as you get close to epsilon, then your W is going to be basically this limit, W of epsilon. And then you extend it smoothly. Like basically, you make it constant, for example. Maybe you need to assume that, I think this is probably OK. But you might have to assume some slightly more regularity for this to be possible. But I think you see what I'm trying to say. So you replace the sigma prime by some other vector field that's actually always unidal, and that's parallel to gamma prime. And then you can actually do that. So basically, between 0 and epsilon, you might take this to be constant if you want. Actually, it doesn't have to be constant. Like, maybe you have to look at the details here. Anyway, you can assume that it's definitely constant near 0, maybe for epsilon over 2 or something. But anyway, you have this vector field, and then now you can do what I was trying to do last time. So, now you can use this WT to be, now you have a vector of the form A WT plus V, and then you're going to take that to something, so V plus, so something that, so let's say a multiple of WT plus a multiple of DDT in such a way that I think what you want to do is you want to put like a minus A here, and then you can construct the B so that, like when you take the inner product of this with your H prime of T, DDT, plus sigma prime of T. I actually did write this down, but I forgot to bring the paper. Then when you do the inner product here, this has to be, oh, sorry, this is the normal, not the tangent. Because you're trying to get a framing. So anyway, you want this to be 0. So then you're going to have A times H prime plus minus, I think that's what it is, and then plus B, and then you have sigma prime of T times W of T. And then yeah, then I think you just set this to be okay, I've done this earlier. It's always harder to do it on the blackboard for some reason. So I think you want to do like H prime, let's see, H prime times W of T here, and then the A will be sort of, okay, so let me write the thing again. So I want sigma prime of T, and then plus H prime of T ddt to be 0. So then I think I want to put the A here. V plus A, and then I have minus A times yeah, and now I think I know. Now I want W prime inner product, sigma prime inner product with W of T, and then I have DDT. Okay. I think this is it. We can double check. I think this is going to work. So I guess, you have to check this is an isomorphism. So, that's kind of why it's, it's a little sensitive. Like you have to actually construct an inverse. But first of all, we, have to check that this falls on the normal bundle. So you have to check that this vector is always orthogonal to this curve, to the curve sigma tilde. So what's the derivative of sigma tilde? The derivative of sigma tilde is h prime ddt plus sigma prime. Okay. So you look at the inner product here. The inner product is going to be a h prime and then this inner product in lower dimensions. And then you're going to have this guy and then this inner product. So that's actually 0. So that's good. So yeah, so there we go. So this is it. And if you want to be, even write it even better, you can say the following thing. So you take some vector z that's here, or maybe I can call it x, some x that's here, and then you take it to, well, what is this? This is what's left of the projection when you project onto w. So this v will be like x minus x dot w, and w depends on t, and then plus, and then now you put this thing. So h prime, and then a w, so that's the part that you project to a, so that's x dot w, and then minus x, now you have the sigma prime. No, yeah, now you have x dot w, and then sigma prime dot w ddt. Okay, so that's another way to write down this thing. And maybe now it's an easy exercise that I can leave you with. Is once you have this formula, then you can invert this, show it's invertible. Basically, this guy is almost always non-zero, but it's 0 exactly at the point t equals half, which is when the derivative here is 0. And the point is that right there, this is non-zero. So you can still find out what a is, basically. Or you can still use this a here to construct this a here. So now it's actually an easy exercise to show this is an isomorphism. But in particular, you see that what's kind of nice that's happening is the orientation. So when you start kind of what's happening with the orientation is when you get close to t equals 0, t equals epsilon, or t equals 1, then this part here will be 0, because sigma prime will be 0. So really, you kind of see, that there is a map from the tangent space to x to the tangent space to x. And the difference is that, basically you're multiplying the term that's in front of w with a function that is either positive or negative. So when it's positive, you're just kind of stretching w by a little factor, which is just this derivative here, whatever it is, 2 or something. And then same thing here with a minus sign. So basically you start with, here's your x, and then you have your w, which is some fixed direction. And then near t equals 0, you're just kind of stretching this a little bit, but you keep the orientation. This map basically just stretches one direction by a positive factor. And then near t equals 1, you do the same thing, but now you stretch it by a negative factor, so you're changing the orientation. And that's why this really, that really gives rise to a framing that coincides with a positive framing at t equals 0 and a negative framing at t equals 1. So that's what we wanted to show. Okay? Sorry this is kind of long, but usually the easy things are long, and it's often faster to talk about harder things. When you have to write down the equations and the calculation, it takes longer. Anyway, is that clear? I'm sorry if this was too slow for you, if you already did it last night. But I think maybe some of you did not. So, okay. And the other thing I want to do before we talk about Morse theories, I want to go back to the proof of the Pontryagin-Thom construction, because I still saw some confused faces yesterday, and I don't know if there are some confused faces on YouTube that I can't see. So anyway, so last time we were so in step 4. So back to the Pontryagin-Thom construction. I said I wasn't going to go back to this, but I changed my mind. So we had this map, capital Phi, that took maps from X Sm modded by homotopy into framed, oriented submanifolds of X, of codimension M, quotiented by framed cobordisms. And by the way, this set, usually people denote this by, they use this bracket notation to denote the set of homotopy classes. Okay. So the last thing that we needed to show, we showed that this was well defined. It doesn't depend on the point that you pick. So it's well defined when you take this quotient. It doesn't depend on the point that you take the preimage, on the regular value, and it doesn't even depend on the choice of bases of the tangent space of Sm. That they're all isotopic, so the framings will be basically isotopic. So the framed manifolds will be framed cobordant. But finally, the last thing we were trying to show was that, so that was the step 4, was that phi is injective. So I said, let's pick two functions, f and g, smooth functions. And let's suppose that we have a regular point, a regular value for both of them. A is a regular value of f and g. And let's suppose that the preimage, that f inverse of A and g inverse of A are framed cobordant. Okay, and then so of course these guys come with the framing that comes from f and g, as I've explained a few times. Okay, so the derivative of f induces an isomorphism from the normal bundle to the tangent bundle of Sm at A, and then if you fix just one basis there, that you can pull it back to the normal bundle at every point on this preimage, and that will give you a basis of the normal bundle, the normal space at each point. So a framing of the normal bundle. Okay? So then I said, so we know that these are framed cobordant. Let's pick the framed cobordism. So, so there is this W, which is in 0, 1 times X. And this is the framed cobordism. So that means that, there is, and I said, we're assuming the framed cobordism is cylindrical. So there's a very easy way, like when you look at the normal bundle of W, that there's an obvious identification between the normal bundle of W and the normal bundle of this guy and this guy. Maybe let me call this Q0 and Q1. I think I did it last time. So basically, when you look at the normal bundle of W, restricted to 0 times X, there is a kind of obvious identification between this guy and the normal bundle of Q0. Okay, so when you have a framing here, that clearly induces a framing here. And when I say a framed cobordism, I mean that the framing is the framing that we had in Q0 from F is exactly this framing. Okay? And then I said, then I used sort of the idea from Riemannian geometry of exponentiating. And I said, well, when we have a framing, then that means that we can pick, we can define an embedding of my manifold. If I have a framing of the normal bundle, then I can use that framing to exponentiate. So I can have this embedding from W times Rk into my manifold X. And the idea is like when I have a framing, I basically have a specific basis that I choose at every point. So I can use this basis, E1, E2, da da da. I can basically take the canonical basis of Rk and take that to that basis and exponentiate using that basis. So exponentiate just means finding the geodesic that has that speed at the time 0 and starts from that specific point on W. Okay, so so let me kind of, so if say this is my W. I kind of have said this several times in the last 2 lectures, but so if I have a basis of the normal bundle, then now I can basically say, given any vector in R2, then I can write this vector as something v1 e1 plus v2 e2. But so that will give rise to, when I take this basis, I don't know, n1 n2. I can look at the vector v1 n1 plus v2 n2. That's going to be a normal vector at the normal space at that point, and then I can take the geodesic with this speed at that point. So that will give me a curve that starts from there, and then I look at the time 1 map of this geodesic. And there's a kind of a result, basically from ODE, that there is a this geodesic flow exists at time 1 if the norm of the vector is small enough. Okay, so then maybe you have to restrict it to a very small tube, but then anyway, for each point there's a little ball where this is true. So there's a diffeomorphism between that little ball and all of Rk. Okay, and you can use you can even use a bump function so that like near 0 you still have the same map, which is basically which has the property that when you take that basically the derivative, or phi star. I can write it like this. So phi star of EI, where EI is the basis of Rk, this really is the eta I of x. So for at x0. So if I take a point in W and then I take the derivative of EI at the point at the 0 here, then I get eta I. So I get the specified framed object. I get the specified guy on the framing. So eta I is are my elements of the framing. Okay, are my bases of the normal bundle. Okay, I've said the same thing kind of in several different ways over the last 2 or 3 lectures. I hope that you understand what I'm saying. So anyway, so the framing will give rise to an embedding like this. And this property will basically say that the map that I'll define into Rm, and then I'll use the stereographic projection into Sm, that map at 0 will have the 0 derivative. That's kind of why you make the specific choice. And then once you have this embedding, basically you just say, if I have a point in the image of this tubular neighborhood, then I just the map into this is not K, it's M. Sorry. The map into Rm is just the projection to Rm. So you just take a point of this form, x, and then a vector in Rm, and I just take it to the same vector in Rm. And then to get to Sm, I just use a stereographic projection. Okay? So the map that we defined, which was that homotopy, if we're doing it for W, I just defined. So I wanted to define a map F that goes from this guy into Sm. So basically what I do is if I'm in this cylinder and I have these copies of Rm, I just kind of first project to Rm. So these are copies of Rm. So first I project to Rm, and then I use a stereographic projection to project it to Sm minus A. Oh, actually, minus, removing minus A. So, sort of I have my sphere, I have my point A. So what I do is I do this stereographic projection like this. Like that. Okay, so there's a formula for this, and this I'm not going to do. I think this you can do. Anyway, so if this is, I was calling this, I think, phi inverse. I think phi was calling this map. So then you can write your expression, for what f is. So your f of z, so this will be equal to, so if z is in the image of the embedding, then z is of the form psi of xu. So basically, I just want to project it to u, but then I want to look at phi inverse. And then outside of the cylinder, I want to just set it all to be minus a. So this is, I kind of already did that in the case of the points when W was just a bunch of points. But it's also true if W is a higher dimension submanifold. It's exactly the same thing. Okay, so now, kind of for each of these guys, as you get close to the boundary or to the infinity in Rm, you're converging to minus a. So outside of this kind of cylinder, with this tubular neighborhood, you can just set it equal to minus a. It's kind of obvious this is continuous, and you have to check something to see it's smooth. But it's true. Okay, I don't think you don't even have to do anything. You don't have to perturb. It's already going to be smooth on the dawn because the stereographic projection is so nice. Okay, so now, basically what this is saying is we had these two submanifolds of 0 times x and 1 times x, and we created this cobordism. And actually, we didn't use anything about f except for q0 and q1. So sort of you have your q0 here, and you have your q1 here, and you have the cobordism w. So now we created a map onto SM on the whole thing that kind of uses this tubular neighborhood on w. But now, if I restrict this to these two slices, to the 0 to the 1 slice, I get new functions. So if I take my capital F and I restrict it to 0 times x, I get what I called f tilde last time. And the same thing, if I restrict to the 1 slice, I get what I called g tilde. Okay, and f tilde and g tilde, you can kind of construct the same way, but now just using the tubular neighborhood induced by the framing on q0 and on q1, which is just a restriction of this embedding here. So it's actually the same embedding still. Okay? So, basically if you restrict the embedding to, sort of 0 times x times Rm, now you have a map from q0 times Rm into, oh, sorry, that was wrong. It's not into x. It's into 0, 1 times x. Because W is a manifold of 0, 1 times x. But anyway, when you restrict it to the intersection with 0 times x, you really get a map just into x. And it's pretty much the same map. It's just a restriction map. And it's the map that you obtain by taking the framing on q0 and exponentiating there. Okay? So basically, you do the exact same thing, and when you restrict f to f tilde, you get exactly the same formula. But the only difference is that now x, instead of being in all of w in 0, 1 times x, you're just on the slice with 0 times x, so you're in q0. Okay? So anyway, so you get these guys, and it's kind of obvious that that a is a regular value, kind of by construction, because this is an embedding, and this stereographic projection is a diffeomorphism. So a is a regular value, and the preimage is exactly the stuff that is taken to 0 here. The preimage of a is going to be, what is basically the preimage is going to be the sets of points of the form psi of x0. So actually for Wn here, so a is a regular value of f tilde and g tilde, and it's kind of obvious that q0 is f tilde inverse of a, and q1 is the g tilde inverse of a. Okay, so again, I'm doing the same thing that I did for the Hopf-Degree theorem, but kind of where the submanifolds have higher dimensions. So I replaced the original functions, but by two other functions that I kind of can clearly construct homotopy using my cobordism. Okay? So that's what I've done so far. And then what we need to show now is that now, this Q0 is, sorry, it's kind of squeezed in the bottom there. But, so basically now I have that Q0 is F inverse of A and F tilde inverse of A. And Q1 is G inverse of A and G tilde inverse of A. This as framed manifolds. So now I need to use this fact to conclude that now F is homotopic to F tilde and G is homotopic to G tilde. Okay? So how do you do that now? Well, I kind of explained it last time, but last time I actually didn't do very much. I just kind of said it in words. I didn't write it down. Again, it's the same thing as the Hopf theorem, but let me write it again, because I did see confused faces, so I did have a feeling that not everybody understood what was going on. So as I said, the idea is to do a linear interpolation. It's to do two linear interpolations. First, kind of near Q0, and then another one away from Q0. So we just know that the preimage of A is the same, and the framings are the same. But we don't know anything else. Like, we don't know even a little bit outside of A. So the first step is to homotope them, to make them equal in the neighborhood of A. And then we're going to homotope them away from the neighborhood of A, so then they're kind of equal. Okay, so what you do is, first you see that in the neighborhood of A, you have the following property. So we had that so now let's just look at Q0. So we had this embedding of Q0 times Rk into X. That's just given by the framing. Okay, so that's the restriction of this embedding. But now we can actually forget about W. Now W, kind of is no longer relevant, because now we're just looking at this part. So now I have the same Q0 and I have this embedding, and basically because and remember how F was defined. No, sorry, you don't know how F was defined, but you know how F tilde was defined. But the point is that because it's the same framing, then that means that, sort of when you look at F composed with psi, and you compose that with the stereographic projection, so that's giving us a map from Rm to Rm. No. This gives us a map from Q0 times Rm to Rm. And the point is that now if you look at, so because of this property here, that means that that when you look at the derivative with respect to these guys, so when you look at the push forward of this with respect, on each of the canonical bases here, that's going to take the derivative of this guy is going to take this EI to exactly the framing. Excuse me. And then the framing will bring this basis to a fixed chosen framing of the tangent space of the manifold here. Okay, so that's kind of how I chose the framing of Q0 using F. So let me write this down. So when I look at psi star of EI, so EI is an element of the canonical basis here, that will bring me exactly to the framing, the ith element of the framing at whichever point I am of Q0. Okay, so this, at whichever point of Q0 I am. And then now, when I apply df of that, df of this guy, by definition, I'm going to get to the ith element of the basis of the tangent space to the sphere. So this is going to be sort of a VI, which is on the tangent space to the sphere at the point A. And I had, I pick a basis here that's fixed, V1 through Vm. That's fixed and doesn't matter on the point of Q0 that I am on. And I can pick whichever basis I want, as long as I just fix one. So I might as well just pick the basis that's the image of the canonical basis of Rm. So when I look at the derivative of the stereographic projection, or the of the stereographic projection map, or the inverse in this case, I can just pick the basis that's going to go exactly to the canonical basis of Rm. Okay, so by just choosing this, by making this choice, I can actually now, so I can suppose that phi star of Vi is actually the canonical basis of Rm. Okay, so all this to say that, by, some kind of obvious, kind of simple choice here that I can make once and for all for how I want to choose my basis of Sm, I basically can assume that this guy here, when I look at the derivative, or what it does to Ei, this is just Ei. In other words, if I look at the partial derivative with respect to U of this guy, at the points x0, so at x0, this is going to be the identity. Okay, so that's really what I wanted to assume. And this is true. All I needed was basically that the framing was the specified framing, and that's the same. And we have the same framing for f and for f tilde. So this equation here is true for f and for f tilde. So then I basically have this property also for f tilde. So the f tilde psi of x0 du is equal to the identity. And then now I can use the Taylor polynomial to say that if the derivative at 0 is the identity, and the map takes 0 to 0 too, and this is kind of obvious that also this guy of x0 is equal to 0. So then this map here, it has the expression. It's basically looking at f in coordinates inside this tabular neighborhood. This guy of xu is going to be u plus something of the order of u squared. Okay? That's just looking at the Taylor polynomial as a function of u. So this guy might also depend on x, but it doesn't matter. It's some because q is compact. This it's really like up to a constant. It's an order of norm of u squared when you yeah. Okay, so it's going to be plus some constant times this. So basically what I want to say is when you take the inner product of this with u, this is going to be norm of u squared, I think, minus c times norm of u cubed. Bigger than or equal to this. Okay, so this is going to be bounded below by this. So what I'm trying to say basically is that if u is sufficiently close to 0, if the norm of u is sufficiently close to 0, then this inner product is positive, unless it's actually equal to 0. So the conclusion is that this map, this is just a local expression of f. When you take the inner product of 0, this is going to be strictly bigger than 0 if u if the normal view is less than epsilon and not 0. Okay? And the same thing is true for f tilde. Because of, we just used the fact that the derivative was 0, was the identity. So the same thing is true for f tilde. If 0 is between maybe there are different epsilons, you just take the minimum. And then now you interpolate between them. Okay? Now you interpolate between f and f tilde, but in these charts. So you can write down your expression. So you choose a bump function, as usual. So you choose a bump function from Rm to 0, 1. This is a bump function supported on the ball of radius epsilon on Rm, and such that rho is identically equal to 1 on the ball of radius epsilon over 2. And then you define h of tx to be, basically, now you look at phi composed with f tilde of x with a t in front, and then plus you do 1 minus t times phi of f. So, this would be your linear interpolation. But then you put the bump function here. And it depends on you. So if x is equal to psi of qu. So, if x is equal to psi of qu, then, if you want, you could actually kind of, if you want, you can put your, maybe to be more consistent with what we have there, we can just write it like this, not write x. So you can see the composition of the three functions here. So you write this, but so this is the linear interpolation in Rm. And then now you have to bring it back to Sm. So you just write down the stereographic projection again. Stereographic projection. Okay. So you did the linear interpolation, but you put the bump function. And then basically, if you're outside of this bump function is supported on Bm. So basically, when you get to the boundary for of this Bm, then rho is 0. Rho is 0. So then you're left with f. So you can glue it by just taking it f, that it's f elsewhere. So it's f of x otherwise. Okay. So why is this necessary? I mean, this is necessary because if you don't do this, then basically you could actually be leaving, like there's no control that that you're not going to be hitting 0 again, and you're not going to be getting more. sorry, what this is doing is basically saying that you, I'm just trying to remember why this is necessary. But so within this ball, you're homotoping like this, and you're making sure that the only places that that hit 0 within the homotopy, that hit A, on SM, which is the same thing as hitting 0 under the stereographic projection, are exactly the points on Q0. So you make this homotopy without changing Q0, without creating any new pre-images in the thing. So yeah, so basically this H is a homotopy, and it starts on F, right? Because for T equals 0, then you just have F. And then it connects F to something that's not F tilde, because outside of the cylinder I'm not F tilde, but near Q0, close enough to Q0, I am F tilde. So it connects F to another function that I'm going to call F tilde tilde, such that F tilde tilde coincides with F tilde in a neighborhood of Q0, and it doesn't hit A anywhere else. So that's actually very important. So that's why we're kind of being annoying and requiring that condition. Because if you just kind of brute force, if you didn't use the row, and you just brute force did the interpolation like this, then maybe the thing that you end up with will actually hit A at other points. It's possible. It's possible that well, you do need the bump functions to be able to glue it to F. Otherwise, you won't be able to glue it to F. But you could have done like a really big bump function and like not worry about epsilon at all. But if you did that, it's possible that within the cylinder, you can create more pre-images of A. I mean, they're going to be cobordant, so they kind of have to cancel out, but you could potentially have other points that are hitting A. And so far, it's not a problem, but I basically want to have the condition that the pre-image of A by this F double tilde is still Q0. I'm not creating any more points in the pre-image of A, or I'm not creating any more pieces of this manifold. And the reason is for what I'm going to do right now. Because what I'm going to say is that in these little neighborhoods of Q0, I'm isolating all the points that are taken to A. So outside of these neighborhoods, I'm mapping outside of the neighborhood of A in SM. Okay? So so I can say this one more time, sort of if you're Q0, you can think about Q0 again as dots. Doesn't really matter. And you have these neighborhoods that are determined by the framing. And they can be kind of large, relatively large. So when you do this linear interpolation, there's no reason that you will not create more intersections with 0 in RM. So if you just do a brute force linear interpolation and you don't worry about this bump function being supported on a ball of radius epsilon, if you just kind of say take any bump function, just means it's supported, the support is compact. So you could have done this procedure, and it would have glued to a smooth homotopy that would satisfy this condition. So it would be a homotopy between F and something that coincides with F tilde in the neighborhood of Q0. But it could also, this map here, this F double tilde, if you don't require anything about it, it could potentially be 0. This thing in here could potentially be 0 in other places that are not just U equals 0. You're taking just a linear homotopy. It could hit 0 at other places. So in particular, when you take phi inverse, it could be hitting A at other points. You could potentially kind of this f tilde tilde could have some other points here in the pre-image of A. Okay? But I don't want that for the next step, as I'll show you. So I don't want that for the next step. So I wanted to, I mean, of course, in the support, it would be equal to, I mean, not in the support. When rho is equal to 1, then it will be equal to f tilde. But between the point where f is identically 1 and f is completely 0, exactly when the bump function is going up and down, right here, you could potentially have new zeros, and therefore new pre-images of A. Okay, and that's why I have this annoying, more technical condition here, because I know that over here I have this positivity when I take the inner product with U, which means that for the whole homotopy, if I homotope here with a bump function and stuff, I still am going to be positive if I'm in this ball. So this condition here guarantees that throughout the whole homotopy, I cannot hit the origin if I am in the ball of radius epsilon. Okay, so that's why I have this kind of annoying condition, and that's why I can conclude that this new manifold that coincides with f tilde in the neighborhood of Q0 has exactly the same pre-image of A. Okay, so once I do that, so now basically I homotoped my f so that it coincides with f tilde in the neighborhood of Q0. And then now I have to continue the homotopy to get all the way to f tilde. So now I kind of have to homotope from f double tilde to just f1 tilde. And what do? Basically now I look at the complement of Q0. So now then I use sort of the opposite stereographic projection. So now I can use a phi bar, which is a stereographic projection that looks at the complement of A to Rm. So this is now the other stereographic projection. And then I can do a linear homotopy there. So I can define an H bar that goes from 0, 1 times x to Sm that takes my Tx to, now basically I look at phi bar composed with f tilde, and then I put a t here. And then I do 1 minus t times phi bar of f double tilde of x. And I do that if x does not belong to phi of q times the ball of radius epsilon over 2. Because I know that f double tilde and f tilde coincide on, they coincide in the neighborhood of Q0, which is exactly this neighborhood here, which is where the support of that bump function was identically 1. Okay, so if I'm not over here, so if I'm over here, they coincide. If I'm not over here, then I know that I'm not hitting A, so I can use this other stereographic projection, and then I can do the linear interpolation there. And so this is why it's very important that I don't hit A outside of this little ball, so that I can apply the stereographic projection, and it has to be well defined. And then now I can just brute force, because the worst that can happen is I can hit the 0 here, but the 0 here is minus A, and I don't care about minus A. Right, so then I have this, and of course I have to do the stereographic projection again. And then I just keep it equal to f tilde or f double tilde, they're the same, if x is in here. So this H bar is a homotopy, homotopy from f double tilde to f tilde. So there we go. Okay? Any questions about this? I know this is long, and in a way, I hope this kind of clarifies even the proof of the Hopf degree theorem. It's exactly the same thing. I think this time I did it a little bit more carefully. And I explained why this condition here is so important. Okay? So, one more time, let me say one more time what we do, and then I promise I'll stop and we're going to Morse theory. But we have these two functions, f and f tilde, that have the same framed submanifold, Q0. And then you want to find a homotopy from f to f tilde. So first of all, you use the fact that the framings are the same to say, well, I can homotope f to something that's equal to f tilde in a neighborhood of Q0. And then I sort of use this other fact to say, okay, now outside of this neighborhood of Q0, then I can homotope it so that they're the same. So you use two linear homotopies, but to be able to use the second one, you have to make sure that you didn't add any new piece of the pre-image, any new piece that gets taken to A by this intermediate map outside of these little neighborhoods of Q0. And that's like a technical fact that you can prove if you take a ball that's sufficiently close, sufficiently small. Okay? All right, so that's it. That basically finishes the proof of the Pontryagin-Thom construction. And in a way, the degree theorem as well. Although I already wrote this down, but I think that some of you didn't understand everything. Maybe I wasn't so clear. Okay. Any questions about this? No? I hope it's clear now. Okay. Well, now we can go to Morse theory. So 3, Morse theory. So I already kind of defined what a Morse function was, I think, but let me do it again. Maybe you forgot. So let X be a manifold, possibly with boundary, and take a function which is smooth. A critical point is said to be non-degenerate if the Hessian, which you can think of as being a bilinear symmetric form, is non-degenerate. Okay, so we have this Hessian symmetric form, and you require that's non-degenerate. This is equivalent to requiring that the matrix of the partial derivatives, so if I write it like this, dxi dxj at P, I guess, is non-singular. But this matrix is only well-defined when you pick charts. So when you look at your function, when you look at a chart, then you can look at this at the second derivative matrix. And that matrix being non-singular is equivalent to this bilinear form being non-degenerate. You can think that the non-degenerate, one of the ways to define this is by just taking, you take this matrix and you multiply by a vector in charts, and then you take the inner product with the other vector. So that will give you this. But then, the matrix itself does not give rise to a linear transformation from TPM to TPM. That's well defined. That doesn't depend on charts. But this bilinear form, this bilinear symmetric form is well defined, doesn't depend on charts. That's why I said it this way. But the condition of being non-degenerate, actually, you can just have stated it like this. Okay, so maybe let's give some examples of non-degenerate points. And I guess I should say that before that, let's just say let's just define what it means for a function to be Morse. F is Morse if all its critical points are non-degenerate. Okay. So that's what it means to be Morse. Okay, so let's give some examples of Morse functions. Well, one way that's very interesting to find Morse functions is if you think of surfaces that are embedded into R3, and then you can look at the height function. Or usually, if you embed a manifold into a Euclidean space, you can project it to one of the R's, and that is often a Morse function. In fact, you can prove using Sard's theorem that if you project along a generic vector, so if you project onto a direction of a generic vector, then there will be a Morse function. So maybe a specific one is not Morse, but if you perturb the projection a little bit, then it'll become Morse. So maybe not necessarily a coordinate axis, but one generic vector, if you project into that direction, that will be a Morse function. Well, you can start with the simplest examples, which is just like surfaces embedded into R3. So here's my sphere. And I think of the Morse function as just being the height function. So this is my function on the sphere. And then you can look at the critical points here. So what are the critical points? There are exactly two critical points. Where are my colors? I think there is only gray today, which is not a great color. But the other colors disappeared. Okay, well, I will just work with gray, white and gray. So I have two critical points. And it's not very, very hard to see that if you take the kind of the usual maps here, and you take some usual chart, that these two critical points are non-degenerate. So these two critical points are non-degenerate. How do you see that? Well, you kind of find a chart, like you can write. If you think about the chart that just takes x and y. Let's define. Let me prove that this point here is non-degenerate. Just to do something, another calculation. You can think of this chart as basically taking a point x, y, z on the sphere to x and y. So what is the expression of phi composed with phi inverse of x and y? So I want to look at the Hessian. So if I'm at the minimum, this will be f of the point x, y, and then minus square root of 1 minus x squared minus y squared. That's for the minimum. So then f is just the height function, so that's just minus square root of 1 minus x squared minus y squared. And it's a simple exercise to see that the second derivative matrix of this is non-singular. Okay? So I'm not going to do the calculus problem, but this guy here, or let me write it like this. This D2, this matrix at 0, 0 is non-singular. Okay? So that means that this guy is non-degenerate, and by the same argument, this guy is non-degenerate, so this is a Morse function. Okay, so f is a Morse function. Okay. So another Morse function in S2 that's a little more interesting is, I mean, if you consider all the other embeddings into R3, then you can have more interesting Morse functions. So another one that's kind of very famous is what's called the heart-shaped Morse function in R2, which is you embed your R2 like this. Like that. I mean, if you want to write down a formula, go ahead. It'd be nice to write. You can write down a formula for this. And then you have the height function. And that it's not very hard to prove that that you have exactly these three critical points, and that they're all non-singular. So this is also a Morse function. Okay, so another example is you can take a surface like the torus and embed it like this. And then you have these critical points. This is also a Morse function. But I guess maybe what's more interesting is what's not a Morse function. So if you take, maybe 4 is a non-example, is if you take your torus like this, like laying horizontally, and then you take, again, this, you always look at the height function in R3. Then over here, what is the singular locus? So what are the critical points? So you see that, the maximum and the minimum, the points where the function attains the maximum and the minimum are always critical points. But here, the maximum is attained on a whole circle. And the same thing for the minimum. So you see, if the critical point comes in a submanifold like that, then there's no way the Hessian can be non-singular. Because in that direction, in the direction, like if you take a point here, in the direction of the Hessian, in this direction, the derivative is always 0. So then the second derivative is going to be 0 too in that direction. Right? So, basically, if you have a non-degenerate critical point, then it cannot be part of a submanifold of dimension bigger than 0. Okay? In a little bit, it's going to be even clearer that the critical points have to be isolated. But I mean, it's clear that they cannot live on a submanifold of dimension bigger than 0 because of this argument. So, if the function is, if the singular locus if the point belongs to a manifold of singular points that has dimension bigger than 0, then you have this problem. You can take a tangent vector field to that manifold, and in that direction, the Hessian has to vanish. The Hessian matrix has to be 0 there. Okay. All right. Okay, so let's talk about the abundance of Morse functions. Kind of, I already told you that, maybe I should write this down. Maybe this is the fifth example. If X is any manifold in Rn, so this is a submanifold, then for almost every A in Rn minus 0, I guess, the projection in the direction of A, so this goes from restricted to X, so this goes from X into R times A, is a Morse function. Okay, so this is a consequence of the of Sard's theorem. I mean, it's a consequence of the Thom transversality theorem if you want, but that's kind of a heavy theorem. This is, it's pretty simple to prove that just using Sard's theorem. And maybe it's like a nice exercise for you. And if you can't do it, you can look in Guillemin Pollack. Okay. But a stronger result that you can prove using Thom transversality theorem is that, I can't remember if I did this or not. I think I did this, but anyway, is that the set of Morse functions is open and dense in C infinity. So the set of Morse functions is an open and dense set. Okay, it's dense by Thom transversality theorem, and it's open because the condition of being Morse is the same as intersecting a closed submanifold transversely. So, it's basically not intersecting a certain closed manifold, which is the closed manifold. I mean, I think I did. I think I did define this in the part about immersions. It's like basically being Morse is the same as the set of F such that the one jet of F doesn't intersect. Oh, I forgot what I called this. Did I call it S1 or? I forgot what I called this. S1, right? Like this? Yeah. And because of dimension conditions, not intersecting is the same as intersecting transversely. So this is the same. I guess I should say this. It's the same as this intersecting S1 transversely. Okay. All right, so now I'm going to prove probably one of the most famous results in Morse theory, which is very simple, but it's kind of what everybody knows about Morse theory, which is the Morse lemma. So this is called the Morse lemma. And it basically says the following. So if I have a non-degenerate critical point, then in a neighborhood of that point, I can find a chart so that my function is basically quadratic. So it says the following. So let P be a critical point of a smooth function that's non-degenerate. Then there exists a chart, phi, which is given as x1 to xn, from a neighborhood of P to Rn, such that, let me write it up there. F composed with phi inverse of x1 to xn is equal to f of p minus x1 squared I equals 1 to k plus xi squared k I equals k plus 1 to n for some k. So basically, you can find a chart so that the function in that chart is just a bunch of xi squareds with plus or minuses. Okay? So this is for some k between 0 and n. Okay. So now let's prove this. Okay, so first of all, we can fix a chart near 0. And now, by fixing a chart near p, so now fixing a chart near p, we can just assume that the chart can take p to 0. Fixing a chart taking p to 0. So now we can kind of compose the chart and just pretend that the manifold, that the function is a function from Rn to R. And then we actually have just a Rio analysis problem. So now, after that, then we can just think that our function, it goes from an open set near Rn, or all of Rn, to R, with the property that f of 0 is 0. And 0 being a non-degenerate, f of 0 is 0, and we also know that f prime of 0 is 0, because it's a critical point. And we're assuming that the second derivative is non-degenerate. So, this is sort of the gradient, if you want. And then we're also assuming that the second derivative is non-singular. Okay. So now I want to kind of use the Taylor polynomial. But the Taylor polynomial would tell me, so I could say that I can write this as f of 0, which is 0. Plus, f prime of 0 times x, and then plus the second derivative of 0x inner product with x, and then plus something of the order of x cubed. Over 2, I guess. Yeah. But, the problem is that then, these two guys are 0. And then I can say, well, I could kind of try to use D2F to change my basis here to get something that's, exactly quadratic. Because this is a symmetric matrix, so I can diagonalize it. But the problem is I'm still kind of left with this guy. And this guy is it's kind of hard to deal with. So instead, instead of having sort of a linear matrix here multiplying x by x, I want to take into account this guy and have kind of a matrix function here, x times x. And I want to kind of absorb this guy into here so that I can do a change of variables that's not linear, but it's like using the inverse function theorem. I can kind of bring this guy in here and actually change the basis to obtain this guy. But not just using like a linear change of transformation, which you can do because this matrix is symmetric, but do something that's a little deeper and uses the inverse function theorem, but actually makes it sort of the identity with signs. Okay, so kind of that's the idea. I think once you understand the idea, the proof is very simple. But if you just see the proof, you might kind of not understand the idea. And I think it is worth looking at this and thinking, this is kind of what you would do. But then you still have this term here that's kind of annoying. That's why a linear transformation doesn't solve the problem that the that the Hessian is not like a diagonal with plus and minus ones. Okay, so yeah, one more time. You could easily do a linear transformation that would, an invertible linear transformation that will make your Hessian really just have plus and minus ones on the diagonal. Because the Hessian is symmetric, so it's diagonalizable. But you'd still not solve the problem with these terms of higher order. So you want to kind of absorb them in here somehow. So what you actually can do, so you can write your function, and I'm going to write it like this, f of x1 through xn, as just basically the sum of xi, xj, times some function hij of x1 through xn, for I and j from 1 to n. So this is what you're going to do to begin with. So in other words, you're going to write this thing quadratically, but at 0, 0, this hij is going to be half of the second derivative, but it's not going to be this linear thing. It's going to have some other terms. So maybe it's not so obvious that you can do this for every function. But the proof is actually very simple. So I claim that you can write the function like this, where hij are smooth functions. And why is that? Well, there's this basically because of the fundamental theorem of calculus. It's kind of how you prove the Taylor polynomial property, but you just kind of do it slightly differently. So, basically you write you can write it like this. So f of t minus f of 0, this is equal to the integral from 0 to 1 of d dt of f of tx ds. Well, let me abuse notations a little bit. It's just kind of annoying to always do keep finding new variables. But anyway, this is the fundamental theorem of calculus. So then this is the gradient of this. So that's going to be the integral from 0 to 1 of df. So sum of df dxi, and then times xi. So okay. So the sum on I. Okay. So now what you can do, so this is 0, Now what you can do is you can kind of do the same thing and integrate from 0 to 1. So now you can look at what this guy is. Because the derivative at 0 is 0, because 0 is a critical point, because of this condition, then you can write this guy as another integral. So this is going to be the sum over I of the integral from 0 to 1. Then you have the integral from 0 to 1 of this guy. So now you have sort of this guy. Well, let me write it like this. dds of df dxi of tsx ds dt. Okay? Because this guy, I'm varying the parameter s from 0 to 1, and at 1 I have this, and at 0 I have 0. So this will be the integral. I guess I can just put the two sums here. So this is going to be the sum of ij, and then I have the integral from 0 to 1, the integral from 0 to 1, and then I have d2f dxi dxj dxi of tsx, and then times the derivative of this with respect to x. So this is going to be times, oh no, and I'm missing the xi. So then I'm going to have times t xj xi ds dt. There we go. So now you see what I want. So now you can write this. This is going to be the sum over ij, and then I have the integral from, or I can write xi xj, and then times this double integral of d2f dxj dxi of tsx times t ds dt. So now this guy here is my function hij of x. All right. And it's kind of clear that if you take the matrix hij of 0, this is going to be exactly 1/2 of the Hessian. Okay? I mean, it's clear in two. You can do it in two different ways. You can just differentiate this guy twice and look at the if you believe this equation, then at 0, you take the partial derivatives, the Hessian, and you're going to get that. Or just using the explicit definition of hij, when you plug in x equals 0, you have the second partial derivatives here that come out, and then you just have the integral of t from 0 to 1, which is 1/2, and the integral of 1 from 0 to 1 is 1. So, okay. So you have this. So this is non-singular. And now, up to a linear change of coordinates, we may assume that h11 of 0 is different from 0. Okay? So when you change the coordinates on x, basically this the Hessian is going to change twice, or it's going to kind of change by a and by a inverse. So basically the Hessian is going to be multiplied by a on one side and by a inverse on the other side. So basically, because this is non-singular, it's you can make sure that the first term in the diagonal is different from 0. Okay? So if you pick one thing, yeah. Anyway, you can even diagonalize it if you want. You can even diagonalize the Hessian. Okay, so now I'm going to write down a change of coordinates that's very, very explicit. So now I'm going to let, So this is non-zero at 0. So this function h11 is going to be different from 0 near 0. So for x near 0. So in a sufficiently small neighborhood of 0, h11 is still going to be different from 0. Okay. I mean, this is even easier. Basically, you have to have a whole column being non-zero. So if one of them, yeah, if all of them are 0, then that wouldn't happen. And if one of them is non-zero, you can just change one. You can just change 2 lines. So anyway, so you have this condition. Then now, basically what you want to do is you want to do something where you turn the first quadratic term into just a square. So you kind of want all the terms involving I and j to be 1 to just be sort of x1 squared, or minus x1 squared. So to do that, we could define new coordinates the following way. So you define, so you can kind of do it by hand actually, it's not that hard. You define x1 tilde to be, so I know x1 has an h11 in front of it. So when I do it squared, I want to just look at the square root of the absolute value of h11 squared, square root. But then I'm actually going to write a few other terms to cancel out all of the xi, x1, xj. So I'm going to write something down to cancel or to absorb all the xi, x1, xj into this x1 squared. So I'm basically I have to look at the other guy. So this is 1 over h11 of x times the sum of h1i of x times xi from I equals 2 to n. So I do this, and then I let xi tilde be equal to xi for I greater than or equal to 2. So then what happens here is when I take x1 squared, or x1 tilde squared, so this is going to be equal to, basically the absolute value of h11 of x times x1 squared plus, now I have basically the sign of the absolute of h11 of x, and then times the sum of, times 2, times the sum of h1i of x, xi, x1. And then I have plus something squared that only depends on xi for I greater than or equal to 2. Okay? All right. So now, if I put that sign here, the sign of h11, so I have plus or minus x1 squared, x1 tilde squared. This is going to be exactly h11 of x, x1 squared, plus, now, the sign, I have twice the number, the sum of h1i of x, x1, xi, for I greater than or equal to 2. And then I have some term that just has xi squared for xi. That's true, xi for I greater than or equal to 2, something like this, some whatever. But the point is that this 2, it actually is already in that formula. So if you look at the terms that are here that have either I or j equals 1, then you have kind of an even number of them. Because this h is symmetric. I forgot to say that. But it's kind of obvious because it's just, because the partial derivatives are symmetric. So the h is symmetric here. So basically, you can, these terms here, if you pick either I to be 1 or j to be 1, you basically have twice as many terms as if you fix, say, I equals 1 and you let the j vary. So basically, these terms here are exactly everything in this formula that involves either I or j equals 1. Okay? So that means that that expression there, f of x1 up to xn, which is equal to that expression there, is equal to plus or minus x1 tilde squared plus a sum of some hij tilde of x of x tilde of xi xj tilde for I and j greater than or equal to 2. Okay? So the one thing that we do need to say that's not done yet is to say that this transformation is a local diffeomorphism. Okay? So if we do say that, then this is a change of coordinates that will where I can write my function, this new change of coordinates like this. So no, I actually, this doesn't make a lot of sense because sort of I don't know that x1 to xn can be written as a function of the x1 tilde through xn tilde. I kind of know that the x1 tilde to xn tilde can be written as a function of x1 of xn because that's how I define them. But I kind of need to show that, I need to say that this is a diffeomorphism, so this is invertible. And why is that true? That's just because of the inverse function theorem. So when you look at this transformation, what's the derivative of this transformation at 0? So this will be, sort of the derivative of this is a matrix that, so it will have, so this guy here, and then it'll have a bunch of other things here. But then it's going to be 0, 1, 0, and then 0, 0, 1, etc., like that. So this matrix is invertible. It's because it's upper diagonal, and the whole diagonal is different from 0. This guy is different from 0. So that means that at 0, I guess you have to do this at 0, then you have this at 0, and this is invertible. So by the inverse function theorem, you can invert that. So this will be, in fact, a new chart. So that means that you can actually write f of x tilde, where x tilde is sort of the new chart, as this. So this is plus or minus x1 tilde squared, and then plus this term of x tilde, xi, xj tilde, for I and j greater than or equal to 2. Okay? So that's kind of the first step of the induction. And then now you kind of do the same thing to come up with, to be quadratic for x2. Okay? So you basically start with, what's the Hessian of this matrix? The Hessian is going to be 2, and then sort of a second derivative here. So 0, 0. And because this thing is non-singular, then you can, up to a linear change of coordinates, you can assume that this guy here is non-zero. And then you can kind of use the exact same thing for, for I equals 1, you don't change. And then for I equals 2, you do this kind of thing. And so you put the h22 over here, and you do this kind of thing to kill everybody after that. And then you will have a very similar situation where this guy here is going to have moved here. And you have a 1 here. So you can have a new, you use the inverse function theorem again to kind of say, now I have, plus or minus x1 tilde, tilde, and then I have x2 tilde, tilde, squared, and then I have the sum of something with I and j greater than or equal to 3. And then you go all the way to n. Okay? So that's the Morse lemma. And just, to be very clear, I think, the first time I saw this, I didn't completely notice, but, this function hij, it doesn't depend only on the xi and xj for I and j greater than 2. The function hij always depends on all of Rn. That's kind of one subtle point. Sort of like you don't have quadratic terms, the quadratic term that it corresponds to has I and j greater than or equal to 2. But this function is still a function from Rn to R at every step of the induction. You can't get necessarily a function of lower dimensions. Okay, but that's okay. There's no problem with that. Okay, it's a function with values in R. But it's always a function from Rn to R. Okay. All right. Yeah, so actually, no, that's true. That's okay. Yeah, even though that's true, you still have a 0 here and here because, so this guy you can differentiate with respect to x1. But then if you don't differentiate these two, then they're going to be, at 0, they're going to be 0. So that's why you still have zeros here, even though this function here does depend on x1, tilde, and all of them. Okay. Anyway, so that's the Morse lemma. Any questions? No. Okay, so I want to give actually another example because I think it's nice. Some other examples of Morse functions, which are non-orientable surfaces. I guess I could have done that before the Morse lemma, but. So I want to give another example that I had prepared, which are non-orientable surfaces. So as you know, non-orientable surfaces are not very easy to embed into R3. But anyway, Sorry. I'm gonna do the examples later. I'm gonna do the examples in the next lecture. Before I wanna just say one important consequence of the Morse lemma. So one important consequence of the Morse lemma is that now, if you have a function, if you have a critical point of a function that's non-degenerate, you know that near this critical point, the function can be written as f of p plus, or you have first I put a minus. You can change the order, but kind of, well, what we proved really is that you have a plus or minus x1 squared, plus or minus x2 squared, etc., plus or minus xn squared. So, usually you change the order and you say, well, I have first, xi squared from I equals 1 to k, and then I have xi squared from k plus 1 to n, up to, a change of order of the variables. So, you have something like this, change order. And then, you know that such a k exists. It could be either 0, it could be n, or it could be something between 0 and n. But this k is very special. And this k is what's called the index of the critical point. So this k is what's called the index of p. And it depends on f. So sometimes you write the function f, but if the f is understood, then you just kind of write the index of p. And you should notice that this k doesn't depend on the chart. And in fact, this k is just the dimension of the negative eigenspace of the Hessian. So you know that your Hessian is a matrix, or it's a bilinear symmetric form. So it'll have, or you can think of, this as two things. So you have a matrix, and then it's a symmetric matrix that is non-singular. So it's diagonalizable, and it can split Rn into into direct sum of the positive eigenspace and the negative eigenspace. So the negative eigenspace will have a dimension, and the positive eigenspace will have the complementary dimension. So that's one way to say it. But this matrix depends on the chart, so it's a little bit annoying. You would have to check that this doesn't depend on the chart. So when you change the chart, you will change the matrix, and these dimensions are preserved. Or you can just say you have the symmetric bilinear map. from a vector space into R. And you have sort of you have the positive part of it and you have the negative part of it. So every symmetric bilinear map, there is sort of a degenerate part, like a zero part, which we know it's zero. It's just zero because the bilinear form is non-degenerate. And you can write your symmetric form as a sum of a positive definite one and a negative definite one. So this would be the dimension of the negative definite part of your symmetric form. So that's a more coordinate-free way to define this K. But anyway, it's actually also the K that comes here. So once you know that your function has this expression by the Morse lemma, then it's easy to check that this K is exactly the dimension of the negative eigenspace, or the dimension of the negative of the space where the maximum subspace on which your symmetric to form is negative definite. Okay? So these are all the same. And just to kind of look at some are the examples that we had looked at before. So if you I guess you can start with something that's even easier than surfaces, which is the circles, one manifolds in R2. So, if I have examples, I'll talk about non-orientable surfaces later. So we can start with circles in R2. So if you look at the circle with the height function, then you have two critical points, this one and this one. And it's not so hard to see that this one, the index, that the function locally, it looks like an x squared. And the function here, locally, it looks like minus x squared. So that means that the index here, so how many negative signs do you have here? You just have 0. So the index here is 0, and the index here is 1. Okay? So, kind of a local minimum will always have, you always have this form here. So at a local minimum, the index is always 0, and at a local maximum, the index is always maximal. It's always equal to n. So, if you have surfaces in R3, so I guess, if you have your sphere, here, you have two critical points. And you see this critical point here, the function looks like x squared plus y squared. So, or I guess maybe x1 squared plus x2 squared. So the index is equal to 0. And here it looks like minus x1 squared minus x2 squared. So then the function looks the index is equal to 2. Okay. So now if you take the heart-shaped function, this point here is a saddle point. So in the expression of the Morse lemma, this will be minus x1 squared plus x2 squared. So here we're going to have index 0, index 1, and then the index will be 2 and 2. Okay? And finally, I guess you can look at the torus, or any oriented surface embedded into R3. You can orient it like this, or you can embed it like this. And then these guys are going to be saddle points. So the function is going to look like this. So these guys will have Morse index 1, and this will be Morse index 2, and this will be Morse index 0. Okay? So, all right, so let's stop here, and then in the next lecture, we will talk about, kind of what we can do, what a Morse function can tell us about the topology of the underlying manifold. Okay? All right, see you in a little bit.